All right, kids, for those of you who like things to be a certain way, this is going to be a little disconcerting for you, all right? We're going to be talking about Lagrange error bound. So, an error bound, okay, is a bound on the actual error, okay? It's not the exact error. So, when we're dealing with an error bound, we have a formula, which I will explain to you because it's going to look confusing, but it's really not that bad. So if you have a Taylor polynomial, some degree Taylor polynomial, whatever, fifth degree, it doesn't matter. So this is some Taylor polynomial. Okay, you know a Taylor polynomial is an estimate, right? Even local linearization is a first degree Taylor polynomial. So we have a Taylor polynomial, and then we have the actual value of some function, right, at a. This is the actual true value, which oftentimes you can't find. So the error is equal to the absolute value, the difference between your approximation and the true value. Okay, that's simply stated. The difference between your approximation and the true value. Well, that error bound, we compute that by using the following formula. Now, this is going to look very confusing, but in fact, it is not bad. So first we have this notation, f to the n plus 1 of z. Well, that means the n plus 1 derivative. So let's say you have a fifth degree Taylor polynomial, then this n plus 1 would be 6. Now, what exactly is the z? Well, you're going to have some interval. Okay, your interval is going to go from the center to a, or vice versa. Center and then a, okay, where you're getting your approximation. So this z is on that interval from c to a, but this value here is the max of the n plus 1 derivative on the interval c to a. So it's the max. You know, when you get when you use extreme value theorem and you're using the candidate test or the closed interval test and you get the max, okay, this is the max. Okay, now here's what's disconcerting. All right, we might not be able to get the max. We might be able to get a max. If we get a max, then instead of equal, this would become less than or equal to. Okay, so keep that in mind. That's what's going to happen. That's going to make you uncomfortable. So anyway, so you get the max of the derivative, or you get the best max. Then you subtract where you're estimating minus your center. You raise that to the power n plus 1. So if that's 6, you raise it to 6 over n plus 1 factorial. That is the formula for Lagrange error bound. Okay, so I'm just going to explain them once more. You need to process it, close your eyes, repeat it, understand it. So Lagrange error bound, if you have a certain degree Taylor polynomial, let's say that degree is 3, your error bound would be the maximum value or a maximum value. Okay, it can be convenient. We call it a safe upper bound. So you take the maximum value of the next derivative, which would be the fourth derivative in this case. You then take that, all right, the maximum value has to be on your interval from the center to where you're approximating or vice versa, okay, on that interval. Then you're going to multiply that by the difference between taking the x value where you're approximating minus your center. So let's say you're approximating at 0.1, right? But your center is 0. That would be 0.1 minus 0. You raise that to the 4th power, and then you divide all of that by 4 factorial. Because remember, n plus 1 is 4 since n was 3. That's it. It's that simple, okay? All right, kids, pause the video, copy down this example. We're going to let f be a function with 5 derivatives on the interval 2 to 3. We're going to assume that the max value of the 5th derivative is of f of x is less than 0.3 for all x in our interval 2 to 3. So this is a bound, okay? It's not exactly equal to 0.3, it's less than it. And a 4th degree Taylor polynomial, t sub 4 of x, all right, is used for f at c equals 2. So that's your center, and we're using this to approximate f of 3. Okay, so first let's identify that this is A, right? This is C. This is your bound. So how accurate is the approximation to the 10,000ths? So the error, okay, would be equal to the max of the 5th derivative at some said value from 2 to 3. It could be at an endpoint. And then we have where we're approximating minus our center to the 5th power over 5 factorial. So this would be the error. We don't have the exact error, so we're going to make it bound by saying it's less than or equal, okay? Now in our case it's going to be less than because it said f, the 5th derivative, was less than. Okay, but normally we're going to say less than or equal to, so I'll just put this in red for you, okay? Normally. Not here though. So this is just going to be less than 0.3 times 1 to the 5th. Well, that's just 1 over 5 factorial. 5 factorial is 120. So when I divide this, I get 0.0025. Okay, so that means that the error is less than that. Okay, that's significant, guys. So who cares about this? All right, well, suppose that my approximation at 3 using my Taylor polynomial of degree 4, let's say that's 1.763. Well, what this means, this amount, means that the actual function f of 3 is greater than 1.763 minus the error, which is less than 1.763 plus the error. So that means that f of 3, the actual value of the function at 3, is an element of the set 1.7605, 1.7655. So guys, even though we can't get the actual value, we know it's in there. Don't you think that's pretty darn good, right? So then they might ask you a question like, oh, okay, could f of 3 equal 1.768? Well, let's look at our interval. 1.768. No, it's not going to make it in. So no, it wouldn't be in our interval, right? You get the idea? Okay. So that's the usefulness behind this, is it the error bound can help us to get a really good approximation. And the approximations get better and better as you get higher degree derivatives. higher degree Taylor polynomials will lead to higher degree derivatives to give you your approximation. All right, here's a typical AP question. We have, pause the video, copy it down, okay, then come back. The function f has derivatives for all orders, okay, for all real numbers, of all orders for all real numbers. Assume that f of 2 is 6, f prime of 2 is 4, f double prime of 2 is -7, f triple prime of 2 is 8. We're going to write a third degree Taylor polynomial for f. Third degree, this is not a series, it's a polynomial, so it's an approximation. So we're going to have f of x is about the third degree Taylor polynomial. Sometimes they'll put it as a p, so I don't want to confuse you guys. So let me have you be used to p as well. Okay, so let's use Taylor's polynomial formula. F of 2 plus, all right, f prime of 2 times x minus 2, because that's the center, minus 7 times x minus 2 squared over 2 factorial. I need degree 3, so I need one more, plus 8 times x minus 2 cubed over 3 factorial. Now we want to approximate f of 2.3. So when we substitute it in, because 2.3 is close to the center, we'll get a good estimate. So you can just type all this into your calculator. We get 6.921. Then they're telling us the fourth derivative satisfies this right here, this bound, for all x from 2 to 2.3. So the way Lagrange error bound works is that the error, I mean, you can just use the word error on the AP exam. That's easier. Trust me, kids got in a lot less trouble when they did that. So we have the fourth degree of z, right, which is going to be on 2 to 2.3 z. Then we have where we're approximating minus our center to the fourth over 4 factorial. Well, we can say that this error, okay, and keep in mind this error, where does this come from? Well, this is f of 2.3, right, subtracted from the fourth degree, the third degree, right, third degree Taylor polynomial of 2.3. That is another way you can write error. So if you don't like the word error, use this, okay? Up to you. Anyway, that has to be bound by, now notice I put less than or equal to this time because this said less than or equal to. So you have to pay careful attention to these silly little details. So that's going to be 9 times 0.3 to the fourth over 4 factorial. I don't need the absolute value here, as you can see. And this is approximately 0.003. Okay, so this is your max error. Hope that helps, kids. I don't think it's too bad. All right, some people will, be dramatic about Lagrange error bound. And you could study this in a lot more detail beyond the scope of this course, but this suffices, and it's a really good understanding. All right, if you understand this, you're in good shape for the AP exam. Thanks, kids.